So for a problem like this, it's a heating curve problem. What you'll do first, I think, is go onto the side here and put in the relevant temperatures. Now you've got in the question here that we're starting at -85.00 and going up to 230.00. So that's going to be our starting point down here. So it'll be -85.00. And up the top here is going to be 230.00. So I think that's good to put in first. The other thing I think is good to put in is the melting point and the boiling point, and those are down here. The melting point will be where the solid turns into a liquid, and so that'll be -50.00 there. And the other one is where the liquid turns into a gas. That's going to be the boiling point. That's 165.00 there. So with that in hand, we can go ahead now and figure out our A, B, C, D, and E. Now for A, anything that's got a slopey line on it, like this here, is going to be Q equals MC delta T, because we're looking at just the same phase, but it's going to just change in temperature. So we're going to have Q equals MC delta T, and I'll say MC solid here. Now the mass is given as 120.00 grams, so we'll put that in there. The heat capacity of the solid is down here. That's 1.801 joules per gram per degree Celsius. And the delta T is going to be the change in temperature here, which is going to be at 35 degrees, or 35.00 degrees. So we're interested in the change here, so there's no need to make it negative or positive or anything else. Just go ahead and just find the difference between them and just take that absolute value. That'll give you the temperature difference there. Now this comes out to be 7564 joules once we take significant figures into account. So that's for A. Now for B, B is a flat line here. So we're looking at the solid liquid phase change, and the way we're going to get that, it will be Q is going to be the number of moles of X multiplied by the delta H of fusion in this case. That's going to be the energy required to turn this from a solid into a liquid. Note how the temperature doesn't change at all during that phase change. So there's no delta T going on here at all. Now the number of moles of X, we need to figure that up first. I'll do that over here. So the moles of X is going to be 120.00 grams of X, and that's times 1 mole over the molecular weight, which is given as 50.00 grams of X. So this gives us, for moles of X, it's going to be 2.400 moles of X. So that's going to be 2.400 mole of X times the delta H of fusion, which is given here as 3.476 kilojoules per mole. So that comes out to be 8.342 kilojoules per mole. But we're going to need everything in joules so that everything can be added together at the end. So I'm going to convert that into joules. We'll do that by multiplying by 1000 joules over 1 kilojoule. And that's going to be 8.342 joules. Now for C, that's another slopey line here, and that's the temperature change for the liquid. So that's going to be Q equals MC delta T, and the C is going to be the C for the liquid there, the heat capacity for liquid. The mass here again, 120.00 grams, times the C of the liquid, which is 3.510 joules per gram per degree Celsius, and that's multiplied by the temperature difference, which will be the difference here between the melting point and the boiling point. So minus 50 up to 165, and the difference there is going to be 215.00 grams degrees Celsius, sorry. That's going to come out to be 9560 joules once we take significant figures into account. Now we've got to be a little bit careful here with the temperature, because it's a difference between 165 and minus 50. So it's effectively 165 minus 50, which comes out to be 215. Okay, so we're running out of room here, so I'm going to delete these here. If you want to see them again, obviously you can go back and take a look at them. So let's see, select. And we're going to now look at D and E. Now D, whoops, let's get a pen here. So D, we're looking at, again, a flat line here. So it's going to be Q is equal to moles of X times, in this case, a delta H of vaporization. Now the moles of X, we found those earlier, 2.400 moles of X, times the delta H of vaporization, which is given as 4.817 kilojoules per mole. This comes out to be 11.56 kilojoules. And we need to convert that into joules, so it's 1000 joules over 1 kilojoule, which is going to give us 11560 joules. And the E here is now going to be this area here, again another slopey area, so it's going to be Q equals mc delta T, the C of the gas. That's going to be 120.00 grams, times the C of the gas, which here is given as 1.213 joules per gram per degree Celsius, and that's multiplied by the temperature change, which is going to be the difference between 230 and 165, which comes out to be 65.00 degrees Celsius. So this comes out to be 9461 joules. Now the question here is asking for the total energy. So what you'll need to do is take all of those energies that we calculated from A, B, C, D, and E and add them together.